I would like to share with you my golden rules for modeling. And this is, of course, not only my work. I got inspired by many of my colleagues and many of the researchers in my field. Okay. First golden rule is model a problem, not a system. If you start modeling a system, you might do lots of interesting things, but it might not lead anywhere. And the reason is that, many things can be relevant for many problems. But what is relevant for your problem? Do you want to improve something? Do you want to find out what the reasons are for a certain phenomenon? If you know what you're after, if you know what your problem is, you are much better able to determine what to include and what not to include. Modeling helps to reason. Use it as a bicycle for your mind. So the model doesn't give you the answers, right? You have to do the thinking. But models can help. Use the power of computation to help you think through things that are just complicated or very many iterations of something. But don't let it replace your thinking. It should help you. But you are the one that should do the thinking. When developing a model, it's often easy to just think, I'll just manage, I'll write this down, I'll just put it in code. But if you are not careful, you cannot think through what you're trying to put down on paper or in your head, you probably also can't code it. So don't think that simply writing it in code will help you solve your problem. Also here, developing the model, you have to do the thinking. Okay, very important one, never trust a single run. Many models have stochastic elements, so every run might be different. And it's very hard to anticipate and to think through in your head whether differences between single runs would actually be relevant for the results that you're looking at. So always make sure that you double check and run multiple instances to just make sure that you're not looking at something that is very unlikely and just happened to be part of this single run. And basically the rule is more general. Never trust a model in the first place. If you don't understand why something comes about, you have to find out. You cannot just say, the model apparently determines that this is the case. If you don't know why this happens, either you have a bug or you have a feature, but you have to find out what the reason is. And unless you can find out what the reason is, you're not done with your modeling. And then in the end, you don't have to trust your model. You trust your own reasoning and your own analysis. This turns to number 5. Your analysis is as strong as the weakest logical link. If there's somewhere a weak spot, whether it's in input data, in a part of the equations of the model, part of the analysis steps, in the validation, in the interpretation, in some aspects that are overlooked, whatever is the weakest part of it, that determines the strength of your overall analysis. So finding a balance between different parts of your analysis, from conceptualization to discussion and interpretation, you have to balance all these things. And this also helps with finding, a balance in the workload. Don't overspend time on one of the aspects, because if you forget about one of the others, all that effort is useless. Number 6, invest in iteration, because you'll use it and you'll need it anyway. Set up your analysis in a way that you can go back, change something, and continue. So that means that you, as early as you can, finish your first modeling cycle with a rubbish model, a partial model, a little bit of a model, a little bit of the modeling that you want, but continue to the analysis phase, to visualizations, to interpretation. Acknowledging all the things that are missing, all the things that are wrong, all the things that are undesirable, and go back and add step by step all those things. And every time keep iterating through the modeling cycle until the end. It helps you in many ways. Not the least for the next golden rule. It also helps you to identify lots of problems and to be consistent about what caused what problems and whether you actually solve them. And the other big important reason why you want to invest in iteration is because you want a working model all the time. It is crucial for modeling morale, and it's crucial for your thought process. Every day try to finish the day with a working model. How poorly it works doesn't matter as long as it functions. It helps to sleep well in the night. Number 8. It's not about model outcomes at all. Although in papers or in reports or in discussions, often discussions lead to and are about model outcomes. But it's not the most important. And experienced modelers will acknowledge this. The model outcomes, they're an end product at the end of the line. And they might be interesting, but it's not about them. It's also not about the model, although you spend all the time modeling, gathering data, doing analyses. It's not about the model. It's about the modeling. It's about that process in which you come to reasoning, come to understanding of system aspects, of things that you hadn't anticipated, of assumptions that appear to be very important. And these little assumptions that appear to be very important, they might be the benefit of your understanding the things you learn about the system or the problem that you're trying to address, the problem you address about the system in the real world. So acknowledge the importance of the modeling and also of the creativity in modeling. If you find a creative solution to represent something very complex in an elegant way, that leads to an interesting model and it might lead to very interesting outcomes. But it's that modeling that is central. Use that process to gain understanding, to learn about the problems that you're trying to solve and about the systems that you're trying to represent. Trade off computation power with thinking. Of course, you can add more computers to the equation here and do more runs and more analyses, but you have to interpret all those findings and make sense of it, and that requires thinking. Sometimes you can take out a whole portion of your experiment simply because it will not lead to a realistic or an interesting scenario. And by simply thinking a little bit through what is relevant and what not, you might reduce a lot of the computational power that you require. Sometimes you need a particular shortcut through a very large design space, and you have a very clear idea of what you want to compare. And if you have a very clear idea and it requires very many runs simply because there's a lot of diversity or the model is slow, then by all means make use of large computer clusters. But balance this, and not for all models required big advanced computers. And the last, and maybe it's the most important for modelers, and it's a very famous one: better be vaguely right than precisely wrong. And the reason is that all models are wrong. That's the famous George Box quote. All models are wrong, but some are useful. Well, the ones that are useful are typically not precisely wrong. They're typically vaguely right. They are good at representing elegantly some aspects of a problem and identifying either solutions or identifying reasons why some aspects of that problem, how they emerge, when they come about, and how you can resolve them. That doesn't mean you have to precisely predict economic growth in 2020 or 2021 or on December 12 of 2035. Better be vaguely right and have an idea about where things are going and how you can intervene, to have a good discussion about this, an inspired discussion, very explicit, and be aware where you are capable of being very crisp with your analysis, and where things are harder and are less precise. It leads to a better discussion, a more realistic discussion, and it also enables you to develop modest but real conclusions. Those were my 10 rules for modeling. If you're willing, if you want to discuss about this, or you have questions, please reach out. I'm more than happy to discuss examples or maybe other suggestions, and look forward to such discussions. Thanks.